Alright, let's determine all extrema, intervals of increase, decrease, points of inflection, and intervals in cavity for the following function. T of x is equal to 2x cubed minus 12x squared plus 18x minus 1. Okay, so we're going to be using derivative testing to gain some insight into the shape and behavior of this function, right? So just off the bat, you can tell this is an odd degree function, right? Because the degree here is 3, so therefore it's a cubic function, it's a positive odd degree function. And we can understand that for a positive odd degree function, the end behaviors would be in the first quadrant and the third quadrant, right? So we'd expect something like, if this is the third quadrant and then this is the first quadrant, you should see that the end behavior should end off like that. You should also expect 2 turns, and a turn is an extrema, right? And the maximum number of turns is equal to the degree minus 1. So we should expect 2 turns, right? So that means, and a turn is a point of extrema, right? But calculus is really useful because we can actually determine what these points of extrema are. Okay, so let's start with the first derivative test. The first derivative test will help us to gain some insight into these points of extrema, but also intervals of increase and decrease. Using the first derivative test, I'm going to find the first derivative. T prime of x is equal to 6x squared minus 24x plus 18. Okay, so to find the points of extrema, we know that an extrema, maximum and minimum point, the slope of the tangent here, the slope of the tangent would be 0. Okay, so that's the premise behind why we let the first derivative equals 0, right? And this process is really useful, especially in optimization, which is in the next section that we will visit. So this is going to give us 6x squared minus 24x plus 18 is equal to 0. What I'm going to do is, to solve for this, I'm going to factor out a 6. So you get x squared minus 4x plus 3 is equal to 0. And if I factor this out, right, you get 2 numbers that add up to negative 4, then multiply to positive 3. So x squared minus 3x minus x plus 3 times 6 is equal to 0. So if you factor these two and these two, you get x minus 3, negative 1x minus 3, and then you factor by grouping, right? So in this case, you get 6 times x minus 1 times x minus 3, and then this is equal to 0. Okay, so having said that, right, this is basically our factored form of our derivative function, and you can notice here that x is equal to 1 and 3 will represent our critical numbers of x, or our x values of our extrema, right? To find the y value, you just plug it into your original function. So your points of extrema should be 1 and t of 1, and 3 and t of 3. Okay, so you plug it back into your original function, and those equivalent points are going to be negative 1. So we have 3 and negative 1. Okay, so your extrema include 1 and 7 and 3 and negative 1. Now we just don't know which one is which. We don't know if which one's a maximum, which one's a minimum. You can actually determine this by your second derivative test, okay, which we will basically be doing out. Now we can also figure out intervals of increase and decrease, right? So if we're looking at intervals of increase and decrease, what I'm going to do is I'm going to plot these critical points. So our critical points or critical numbers are 1 and 3. So in this case, I'm just going to plot a 1 here, and a 3 here. This is negative infinity, it's positive infinity. This isn't to scale, right? And for each interval, so we can notice here that in between the critical points and our positive and negative infinities, we have our intervals. We have negative infinity and 1, so this is one of our intervals. Then we have 1 and 3, that's the second interval, and the other interval here is 3 and positive infinity. Okay, so between each interval, we're going to plug in some points and test to see what our intervals of increase and decrease are using our first derivative test, right? So, so let's start with our first interval between negative infinity and 1, right? So let's do, and we know that our first derivative function f prime of x here is basically 6x minus 1, x minus 3, okay? And let's start with our first interval, and let's say we were doing f prime of a number in between negative infinity and 1. Let's do f prime of 0. Okay, f prime of 0, you're going to get 6 times 0 minus 1 is a negative, so negative 0 minus 3 is negative 3, and then 2 negatives, you're going to get a positive, right? So 6 is also positive, so you get a positive in general. So this is an interval of increase. Okay, so there's an interval of increase. I'm going to show this with an upward sloping arrow. Between 1 and 3, I'm going to say x is 2, so I'm going to plug in f prime of 2. And in this case, you get positive, positive, negative, so this is negative, and then as a result, you have an interval of decrease. And using the first derivative test, you can notice here that at 1, right, what you should see here is it should be concave down. Okay, so this is actually a maximum. So this is our local maximum. The reason I'm using local is because, you know, this is a degree of 3, right? So we actually have a local maximum here. Then between 3 and positive infinity, let's do f prime of 4. If I do f prime of 4, you get positive, positive, negative, and in this case, positive, positive, and positive, because 4 minus 1 is 3, and 4 minus 3 is 1, so you should have an upward sloping arrow, right? So there's an interval of increase, and you can actually notice that if you look at the concavity, you guys are shifting from interval of decrease to an interval of increase, right? At the critical point, here you should see a minimum point. So this is actually a local minimum. Okay, so when you shift from interval of increase to decrease, then it's a maximum. Okay, so this is how you can actually determine if you have a maximum minimum point. Now you can also verify this using the second derivative test, right? But it's nice to kind of see it more than one way. So now we figured out our extrema, we figured out our intervals of increase and decrease, right? So our intervals of increase occur at x belongs to negative infinity and 1, as well as 3 and positive infinity. We also found that our intervals of decrease occur at x belongs to 1 and 3. Okay. Next thing we want to do here is we want to figure out intervals of concavity and the points of inflection, right? So let's look at our second derivative test. Okay, so I'm going to do my second derivative test. Okay, so if I'm looking at my second derivative test, we know that our first derivative, f prime of x, is equal to 6x squared minus 24x plus 18. So our second derivative, I think it was, instead of using f, I should have used t, but it's really the same thing, right? So, but let's be consistent, right? So this is t prime of x was 6x squared minus 24x plus 18. So t double prime of x, the derivative of your first derivative, is equal to 12x minus 24. Okay, so using our second derivative test, let's figure out our point of inflection. So a point of inflection occurs when t, the second derivative, is equal to 0, right? So in this case, 12x minus 24 is equal to 0. I'm going to move the 24 to the other side. 12x is equal to 24. X is equal to 2. So we have a point of inflection at x is equal to 2, right? And that's just the x values. To find the y value, so we know that's 2 and t of 2. Okay, so let's figure out what that equivalent point is if we plug it into the function. So t of 2 here is 3, so we get 2 and 3. So at 2 and 3, we have a point of inflection. Okay, so that's a key point to understand, the point of inflection. And using a point of inflection, we can actually identify intervals of concavity. So to do that, I'm just going to create a table here, a number line. Okay, so we have a point of inflection at 2. This is negative infinity, and this is positive infinity. Using this point, this number line, we can figure out the interval. So one of the intervals is negative infinity and 2. The other interval is 2 and positive infinity. We can understand that a point of inflection is a change in concavity, right? So at 2 and 3, we actually do get a change. Now let's take a look at negative infinity and 2, right? So I'm going to do f second derivative, f double prime. We'll pick a number between this interval. Let's do 0. F double prime of 0 here, if I plug this into my second derivative function, we basically get 12 times 0, which is 0 minus 24, which is negative. So this is less than 0. So if the second derivative is less than 0, and instead of saying f, we should write t. Right? So I guess I'm just so used to writing down f. So you get t double prime of 0 is less than 0, and as a result it's concave down in this portion. Okay, so it's concave down in this portion. Now t double prime between 2 and positive infinity, let's try 3. If I plug in 3 here, so you plug in this into the second derivative function which we had here, right? So you're doing 12 times 3 is 36 minus 24, it's positive 12, so it's greater than 0, so it's going to be concave up. You can see that there is a change in concavity from concave down to concave up at x is equal to 2, right? So this is basically the idea, right? So these are our intervals concavity, this is our point of inflection. We can also use the second derivative test to verify our extrema, our maximum minimum points. We stated earlier that our extrema, according to the first derivative test, were 1 and, we had it up here, 1 and 7. And the other extrema here was 3 and negative 1, right? So these were extrema, and we said that 1 and 7 here was our local maximum, right? That's what we said here, and 3 and negative 1 was our local minimum. So this was our local maximum, and this is our local minimum. Well, to verify this, these are critical points, right? We can test it with the second derivative test. If I do f double prime of 1 here, we basically will get 12 times 1 minus 24, and that's actually less than 0. So it's actually concave down. Because it's a critical point, then this should be a maximum. So that is verified, right? So if we do f double prime of 3, this is actually the value that we tested. We actually will see that this is going to be greater than 0, so this is concave up, and then this point should be the minimum, right? So this is verified. And sorry guys, this was, instead of f, we should be looking at this as t, right? Once again, it's just the name of a function. So it's t double prime of 1, t double prime of 3. So that's how you can use derivative testing to glean a lot of information